Okay, we're live now. So everybody out in TV land can see us, which means the other 300 people in the class taking it online. So I want everybody here to wave at them. Hold on. Okay, everybody. Hey. Okay. Hello out there. I'm going to turn on Q&A, and I would I'd appreciate it if someone out there, if they can hear what we're saying, that they post a question saying, yes, I can hear. The first post is, I'm not seeing questions. So you're right. You should be able to hear it now. There's a lag of a couple minutes between what I say here and when you see it. Anyways, today I'm going to start with the first of several. Yeah, thanks. I'm going to start with the first of several lectures on decision trees. There's going to be 3. This first one is kind of a demo of decision trees, and then some examples of how to use a decision tree if you have it. Once I finish that, so I expect it's not going to take the whole period, I'll try to allot some time to, on campus here, talking about the lesson about how to assess learners. But right now I'm going to focus on decision tree learning. Now, decision trees can be used for classification and regression. And as a way to sort of demonstrate decision trees, I have this fantastic piece of technology. Has anybody seen one of these before? No? Okay. You've seen one, really?
Yeah. Isn't that called a bee feeder?
A bee feeder?
Yeah, it's a type of gin.
It is a gin. Yes, okay. You probably haven't seen this gin. I didn't even know it was related to something real. Okay, you may be wondering, what is it? Okay, well, packed into this little piece of plastic is, huh?
Candy.
What? Candy? Oh, yeah. It looks like it. It's well, so I had never seen or heard of this thing until we were shopping at Walmart one day, and my daughter made me buy it. It's like, okay, all right, okay. Just to get her to leave me alone, I bought it. It's like $20. Anyways, she started playing with it, and I was amazed at what it could do, and you'll see in a minute. But anyways, it has the ability to synthesize speech, which really means it plays recorded messages. It can understand speech, things like yes and no, and it can reason to some extent. Now, who's heard of the 20 questions, the animal guessing game? You ever heard of that? Well, here are the rules. I think the traditional American version is one person. We do this a lot when we're like driving cross country and trying to keep the kids occupied, right? Like long road trip. Anyways, one kid thinks of something, and then the other kids get to ask a question one after the other to try and figure out what it is. And they have to ask a yes or no question. As an example, the game that this one plays is it plays essentially the animal guessing game. So you, the user, think of an animal, and then it asks you questions like how big, is it bigger than a microwave oven? All the questions are sort of binary questions. It's bigger than a microwave. Well, you'll hear the questions in a second. But through this process, it eventually figures out which animal you're thinking of. Okay, now, to demonstrate this, I need a volunteer from the audience. I have randomly selected 3 potential animals, and I need a volunteer to select from these random animals. So you, sir, come on down. Okay, all right, well, okay, I'll raise them up one at a time, and you tell me when to stop.
Stop.
Okay, all right, let me shuffle them first, all right. Okay, we'll go again.
Stop.
Okay. I should, to make it more fun, I should have another volunteer open up the envelope. But I'll just.
Oh, I'm not.
Okay. All right, come on up. Yeah, it'll be even more exciting. Now, as far as you know, I put the same animal in all three, but I promise you.
Is this gonna air on like NBC later, like on TV? Should I talk about
Just YouTube. But so show it to the. I won't look.
Okay.
Well, you know what? I have to look. Okay, never mind. Show it to them too. The reason I have to look is because I'm going to answer the questions. Make sure that the camera there. Oh well. Well, we don't want this thing to hear because it would be cheating. So.
Sure. So nobody say it.
Okay. Okay. Now we'll play the game. Thank you.
Hey there, buddy. Want to play? Great! I love guessing games, especially when I'm sure to win. Think of an animal. Say, okay, when you're ready.
Okay.
Super! I'm going to ask you a question. Answer yes, no, or I don't know. You can also say, it depends.
Okay.
Does it have hair or fur?
Yes.
All right. Does this animal mainly eat plants, grass, and fruit?
Yes.
Okay. Does it live mainly in Africa?
Yes.
Very interesting. Does this animal live in the forest?
No.
No.
Aha, I see.
What do they call it in Millionaire, where you call out for?
Does it have hooves?
Yes.
Yes.
Does this animal have horns or antlers?
Yes.
That's what I thought. Is this animal very big?
Yes.
All right. Is it friendly?
Yes.
Okay. Does it have spots?
Yes.
Very interesting. I know. Don't tell me. If my magic powers aren't mistaken, you were thinking of a giraffe.
Yay!
Am I right?
Yes.
Wow. Good. One more round.
Okay, I won't subject you to another. No.
Think of an animal. Okay, when you're ready.
Oh, we have secrets. Pull up the battery kind of thing. Anyways, my daughter memorized all of its sayings and so on. So like when we play 20 questions in the car, she's speaking with that accent. Okay, now that's to be honest, I'm not certain that inside this thing it uses a decision tree. I think it does, but at least that's consistent with the sorts of the way it behaves. But I'm going to tell you how we could build a decision tree to solve this problem. Yeah.
Before we move on, if we do get some of the questions wrong, how good is it still getting what you?
In my experience with this thing, if you get the question wrong, then that session it degenerates into it. I mean, it continues going on, but it gives up. One thing that's interesting about it that is not well, one of the optional answers is I don't know, or it depends. So in some sense, it's if it is using decision trees, it actually is using decision trees with potentially 3 outgoing edges. Yes, maybe, or yes, I don't know, and no. But forget that for now. We're going to focus on binary decision trees. But let me, so let's, I'm going to move the camera over to here. I think I'll have to disconnect this. Okay, somebody says they can hear us. That's great. We have 18 viewers. That's awesome. So I'm going to be switching back and forth from writing on the board to looking at my computer. So just bear with me when I do that. So if you think about this, the decision tree that this thing was using, and you try to figure out, what's inside it. Well, one thing it's got is a list of factors, right? So those are quantitative metrics that we can check and ask questions about. Sometimes they're binary, so like, does it have spots? So let me list a couple of them. I'll call X1 skin texture. So that's like fur or no fur. X2 might be spots. It asks frequently asked questions about size. So the three sorts of questions I've heard it ask. Let me say particular answers over here. So the three questions it asks about size are: is it larger than a microwave? Is it larger than a washing machine? And is it very large? Or something like that. So essentially we have microwave, washing machine, size, and very large. You get the idea. So in its system somewhere, it has a number of these factors, and then it asks questions regarding them. Now, my hypothesis is, I'm going to move to the side a little bit here. Is that internally, it's got a decision tree for evaluating, for asking questions and evaluating these issues. So decision tree works like this. It's composed of nodes, and there's two types of nodes. There's decision nodes and leaves, okay? One of these nodes is the root node. And inside each one of these decision nodes is essentially a binary question. So let's say it's going to ask a question about factor 1. So we would need to create some sort of data structure that remembers, oh, this question is about factor 1. And then there's some sort of value that you split on. So in this case, it's essentially fur. And if the answer is yes, we go down this way. If the answer is no, we go down this way. And we continue now down to another node, each direction. And in our case, we had fur. So maybe this next one is X2, spots. And yes, and no. I'm going to make sort of an abbreviated tree just for the purpose of this discussion, because we're going to have some more detailed trees in a moment. But let's say we only studied a few animals, and the ones that have fur and have spots, those are always giraffes. And the ones that have fur and don't have spots, those are, say, buffalo. And similarly, we might have more branches down this right-hand side, and these last nodes are our leaves. Now today I'm going to focus on talking about the structure of a decision tree and how to use one if you have one. But the next lecture is going to be about suppose we have the data, how do we build a tree from that data? So like I said, today we're focusing on how to use one if you have one. But anyways, I wanted to identify these key parts of a decision tree. Let me pause for a second, see if anybody's got any questions. I'll check online too here. No questions. Okay. All right, let me get my notes over here. So let me just formally write down again the what makes up a decision tree. So a long time ago, does anybody here take a course with Professor Variest and ECE? Anyways, long time ago, I took a course on information theory with him, and he could write on the board faster than I could write my notes. So he was just like, anyways, you're not going to have that problem with me. But anyways, I couldn't both keep up with him taking notes and understand what he was talking about. So eventually I just quit taking notes and tried to understand him. But anyways, because I take notes so slowly, I suggest, or because I write so slowly, you can take notes. Okay, so what makes up a decision tree? Okay, a list of factors. And these are our X's. And again, there might be many of them. Might be X1, X2, X3. Then the answers, actually the correct term for that doesn't occur to me right now, but labels, that's the right term. Okay. So this is our Y. So that can either be a label like giraffe, or it can be a label like 2.3. Could be numerical if we're building a regression tree. Then we have a set of nodes, and each node includes the factor used, and what I'm going to call a split val or split value. So we're looking at a particular value, and then we're going to go one way down the tree if it's less than or equal to that value, and another way down the tree if it's greater than that value. And also, coming out of the nodes are essentially edges pointing us to the next nodes to the left and the right. Oops. Okay, one of these nodes is designated as the root node. And then finally, we have our leaves. Okay, does everybody get that? Those are all the things you need to define a decision tree. Okay, now I'm going to give you a concrete example of some data we can work with. And actually, for the decision tree assignment that's coming up, we're going to use this data. Excuse me. I love it when it does that. Okay, there is at UC Irvine, there is a group of people and a website that's dedicated to providing data sets for machine learning testing. And they have a famous suite of many different types of data. And the one that we're going to use is one concerning wine. Let's see. And I want to go ahead and cite, properly credit the people who created this. So I'll do it again when we issue the assignment. But anyways, this is from a paper in 2009. Data set is created by Corderia. Anyways, they're Portuguese people. And it turns out that they did the tests on port wine. So that's the reason for the connection. Probably, I'm guessing, like on a grant from the Port Wine Federation of Portugal or something. Anyways, thank you for your data. Okay, let's talk about the data. Or more properly, what they were trying to do. So I'm making a little bit of this up, but it's consistent with what I've read so far. But they were looking for quantitative, sort of automated ways that they could evaluate the quality of wine. So what they did is they got a number of volunteers to taste several different wines. I'm not sure how many different, but probably tens or more. And they asked each person to score each glass of wine on a scale from 0 to 10. Then they separately measured for each glass of wine 11, I think 10 different quantities, things that they could just shove into a machine that could measure them chemically. So here are some of those factors. Fixed acidity, volatile acidity, I'm not sure what the difference between that is, citric acid, residual sugar, chlorides, and so on. And then, so these first factors are our X's, and then this last one, quality, is the Y that we're going to use to train our system. Now, short quiz. Which of these factors do you think is most strongly correlated with the volunteer's perception of quality? I'm deliberately not showing you all the factors.
Residual sugar.
No. But good guess. Somebody else make a guess. One more guess. Why do you drink wine as opposed to grape juice? Right. Of all these factors, percentage of alcohol is the most strongly correlated with the people's judgment of quality. Now, it may be that it just happens, it's not necessarily that that's causality. There may be other factors that are related to alcohol as well, but just pointing that out. Okay, so let's look at this data a little bit more now. In fact, I have another view of it over here. Each row here represents the value of each of these 11 factors, and then why the judgment of the person, so each row represents one test. So let's suppose for a moment I'm going to map this to the S&P 500. Each row might represent the value of factors of each stock on a particular day. And then Y might represent the return several days later. So what that means is for each day we have 500 individual rows, one for each stock. Coming back to the wine, each row is one person tasting one wine and their assessment over here. Now, one thing to keep in mind is there may, many people tasted exactly the same wine. So we're going to have a row for each person. So we'll have multiple rows for each particular wine where the X's will be the same, but the Y's might be different. That makes sense? Now, just for fun, I used the Excel's correlation function for each factor to look at how strongly correlated it was with our Y. Excuse me. So you can see here, factor 11 has a correlation of 0.47 with quality. And that's not, if you're an engineer, you might be thinking, okay, I don't want to build a bridge with a 0.47 correlation with, that it won't fall down. So that's typically a weak relationship for many uses, but for machine learning, and especially classification and regression and so on, that's a fairly strong value. Now, note that some of these are negative, like this one, negative 0.391. What that means is essentially is that the larger, in general, the larger this number is, the the lower the quality. It doesn't mean it's not a good factor for evaluating. It just means that it's inversely related. Okay, so that's our data. I want now. I'm going to take a moment to draw a decision tree, and then I'm going to give you some example data rows, and I want you all, from my excellently drawn decision tree on the board, I'm going to ask you to figure out what that decision tree says the quality of the wine should be. Okay? Before I do that, let me back up a little bit. The process for utilizing decision trees is the following. You start with data like this. You use that data through some mysterious process that you'll learn next week to build a decision tree. Then once you have the decision tree, you can now query it. So you can say, okay, I have a wine with these different factors. What do we think a human will say the quality is? And then we consult that tree, and we end up at a leaf, and that's what we estimate the quality to be. And by the way, I skipped over it, but presumably the utility for that is they can very quickly and automatically evaluate the quality of a wine without necessarily having to have a human taste it. So they can, essentially they're putting some poor bastard out of work who spends all day tasting wine. But it also, though, provides a more objective measure of the quality of wine. Okay, I'm going to take a moment to draw my decision tree on the board, and in the meantime, we'll have an interlude of elevator music. So I'll be back in just a moment.
That's what we're going to have to do. But yeah, just look. That doesn't raise the line. Because this is acceptable. Because funding costs when you teach your friends first. That is first.
Okay, so online, you all should be able to see the tree I drew up. If not, complain with a question, please. Anyways, I realize for some of you in the back, it may be hard to see unless you have really good eyes, but tried to draw it as large as I could. Anyways, each one of these is a decision node, and if the answer to the question we ask in each one is yes, we go to the left. If it's no, we go to the right. So for instance, this decision node, which is the root, asks, is factor 11 less than or equal to 10? And if it is, we go down here, and we ask about factor 2, and so on. Anyways, as we ask each of these questions, eventually we reach a leaf node, and boom, that's our answer. Now, a couple things to point out here. We don't necessarily use all factors in a decision tree. Sometimes some factors are just so predictive. In fact, sometimes for some data, you might have 10 factors, but only end up using one of them in your decision tree. Now, you might still have that factor, like for instance, we have factor 11 twice in this decision tree. You might have it at multiple levels within the decision tree, and it might be repeated, for instance. Now, note if you go down, say, this path, you use factor 11, 2, and 8, but you don't use factor 10, for instance. So anyways, I'm going to put up a example piece of data and have you use this tree and tell me what you think the value is. So what do we need? We need factor 2, factor 8, factor 10, and factor 11. Right. So we're gonna query the tree. Right. So okay, so these are the values of our 4 factors that make up this tree. I want everybody to take a moment themselves and try and figure out what does our model think the quality of the wine is. Okay, raise your hand if you're done. Okay, we'll wait longer. How about you in TV land? Who wants me to work through it? Okay, I'm confused. Okay, so you're not finished, but you don't want me to work through it. Let me ask again. Who's worked through it? Okay. Where are you stuck? Yes. Okay, so you have worked through it. Okay. All right. What's the answer? Yes. So, working through it. Our first question is about factor 11. Is it less than or equal to 10? Yes. So that's predictive of a sucky wine, right? Because, well, I know because I looked at the data here. 10 is about the medium, that's the alcohol level is 11. 10 is about the median value of alcohol. So if it's less than 10, we're probably headed towards suckiness. Okay, factor 2, is it less than or equal to 0.5? No. So we're down here at this node. Factor 8, is it less than or equal to 1? Yes. Boom, answer is 3. Okay? So that's how we query a tree that we have. Now, I'll look in my example data and tell you what the real answer was. Well, the real answer was 3. So a human who tasted the wine actually also evaluated at a 3. Now, I, for the most part, just kind of invented this decision tree, but I built it from a few examples. So we're lucky that it turned out to match that. But here's something for you to think about. Let's suppose we take half of our data and we built a tree like this. In this case, I think there's 1,600 rows, where each row is one sample. So let's suppose we took 800 of those examples and built a tree. Now, most ways of building a tree, if you build an exact tree, which an exact tree means that each example is represented in one leaf, right? So if we took 800 samples, we would build a tree that had 800 leaves. Now, suppose we query that tree with one of the data elements that we use to train it. Who thinks it would give us exactly the same value we trained it with? Yes? Well, the answer is yes, because because of the way that we build the trees, we're guaranteed that if we query it with any of the samples from the training data, we'll get exactly the answer that we trained it with. So that's called in-sample testing. Okay? Now suppose we took the other 800 samples and we queried the tree for each one of those samples one at a time, and we compared what our tree thought the correct answer was with what was recorded in our data. How could we evaluate whether our tree was making good predictions or not? So let me put it another way. The result that we get out of this test is, so we have Y, I'll call it Y test, and Y, what do we usually call it, Dave? The true one?
Actual.
Okay.
Test is what we.
Oh, predicted and test. Okay.
Predicted and test.
So Y test is the number that our model thinks that particular data element is, and Y test is the value that we know already. We hid that data from the system, and now we're testing to see how good it is. So what if we, let's say our predict is 3, our test is 3, 4, 3, 5, 4. So say we're making a prediction and then we're comparing it to what the actual data was. What sorts of values would you like to see in these columns if your model is working well? Right, right. Or another another way to think about it is you would like the values, the pairs of values in these columns to be correlated. So what's the best correlation we could have? What would indicate that our model is perfect? 1. That's right. Okay. Okay. So that's and we'll talk later about how to assess models, but that's an important one. Now, you're very rarely going to have a correlation of 1 when you test your data out of sample, but sometimes for certain problems it happens. Okay, I'm going to switch back to, well, no, I'm not. Let's see what we see here. Okay, in my laptop so I can see something here. The last topic I want to cover today on decision trees is I want to present to you a data structure that you can use to build and store your decision trees in. There are lots of different ways to do it. A Java or C++ programmer thinks object-oriented, and they want to make a node class, and each of these nodes an instance, and link them all together. That's okay, but it ends up, especially for large data sets in Python, it ends up being really slow and burns up a lot of memory. You can do it in Python, but what I'm going to suggest to you is a matrix or an array-based representation that ends up being really, really fast. Now, if you're determined that you have to do it in an object-oriented manner, that's okay, but please try my way first, and then do your object-oriented approach, because I think once you get into it a little bit, you'll discover that my recommendation is pretty easy and fast. Okay, so here is the data structure. And the data structure is it's an ND array with 2 dimensions. I gotta write smaller. Okay, so each row in this ND array corresponds to one of our decision nodes or a leaf. And so let's start with this one. I'll use a different color. So, oh, and by the way, these little blue numbers are labeled to correspond to the rows that I'm going to fill them in over here. I did that as a little cheat to make this part of the lecture easier. But anyways, in this first row, row 0, the factor that we're going to use is 11. The split val, or the number that we're going to make our comparison on, is 10. And if, when we're querying, and by the way, this first row is always the root. And if we're querying the root and the value of factor 11 is less than or equal to 10, this column tells us which row represents our next decision node. So I've labeled it there, it's 1. And if we go to the right, it's 8. Does everybody get that? Okay, now, the rest of the rows are going to be split into essentially 2 groups. So one set of rows is going to represent the left tree, and some other set of nodes are going to represent the right tree. So these guys over here will be packed into this part of the array, and these guys over here will be over here. That make sense? Okay. Let me flesh this out a little bit more. Okay. Now I don't know if I estimated the length here correctly, so I'll draw it back later. But before one additional thing I want to tell you, the way that we represent leaves in this data structure is we use a special number to represent the factor. We use -1. So if we get to a row and the factor is -1, that means it's a leaf. So anyways, let me real quickly fill this in. Now, how many rows should we have? Who knows the answer? 11, right? And that's because there's 11 nodes over here, right? Okay. I know that was easy, but just checking. Oh, I screwed up. So with the magic, I'm not going to do that. Okay. Sorry about that. somehow I ended up losing a row here. Oh, no, we got 11, okay. Anyways, I'm not, it's going to be too tedious to fill all this in, but let me just highlight a few things about it. So the left branch of this tree is represented by nodes 1 through 7. And of course, the right by 8 through 9. So this is here. And this one over here. Now, something to observe is each of these subtrees is itself a tree. The root node is of the left tree is that first row. And then its left tree is right here. So this part is that, right? And then we have 2 leaves here, right? So does everybody get the structure, this data structure? Any questions about the data structure? We're going to blaze into it more on Tuesday. Let me. I should fill in a few of these numbers on the left here because I want to illustrate something. Let me fill in just the top couple. Okay, so let's look at this for a second. So coming into the root node, if factor 11 is less than or equal to 10, then we go to node 1, which is the next one. Otherwise, we go to node 8, which is way down here, right? So that redirects us to look at the right part of the tree. Similarly, so we went down this left branch. If factor 2 is less than or equal to 0.5, we go immediately to the next row. That's our left tree. Otherwise, we go to 5, which is down here. Anyways, a couple things to point out. So the number here is essentially the index to the head of the next tree to look at, or the root of the next tree. Now, when we have a leaf, it doesn't really matter what values we put in here because we're never going to use them, right? We're at a leaf, we're done, it's terminated. I put -1s in there just for reference. Anyways, the way I've shown this data structure here today, these are absolute references into this array. You could, if you wanted to, instead make them relative. Now, why is that? Well, when you're building this tree, it's a recursive process, and like I said, we'll get to that soon. But it's often convenient when you're building it. When when you recurse to build the right tree, if the, when you recurse to build the left tree, if it just pops up and tells you how big is the left tree, then you know immediately that however big the left tree is, that's how far down we go to start the right tree. You don't have to worry about that too much right now, but as an example, look, we know the right tree starts at cell 8 here, and that's because our left tree has 1, 2, 3, 4, let's see, 1, 2, 3, 4, 5, 6, 7 elements, right? So we just know immediately to go to that point. Similarly, here this is an absolute reference to 5, but really, if we wanted to store a relative number there, we could use 1, 2, 3, 4, and that would get us there if we're going to use relative. Just keep in mind that you might want to use relative numbers for references to those rows instead of absolute. Okay, just a couple more things to cover today, and then I'll take questions. Okay, a couple things I wanted to highlight and ask you some questions about. First of all, first question, which learning method of the 3 that I'm going to list do you think is fastest? K nearest neighbor, decision trees, or linear regression? Way in the back there.
K nearest neighbor.
No. Well, okay. I didn't give you enough information. The question that would be reasonable to ask me is, well, do you mean the learning part or the querying part? So let's for now say I'm asking you about the querying part. Okay, you can go again.
Decision trees.
No. Okay. Once you have the model, the fastest learning method is linear regression. Because think about it. How do you calculate the prediction? You got 3 x's or whatever. It's one parameter times x1, another parameter times x2, another parameter times x3. Add them together, boom, you're done. So that's linear regression. For K nearest neighbor, you have to go consult your 1,000 data elements, calculate the distance from your query to all of the other data elements, and then find the closest 3 or 5 or whatever your K is. So you have to calculate distance to all of them, sort, and then take the mean of the ones that are closest. So K and N at query time is really slow. Okay, I'll give you one more chance. Well, another question. Let's suppose we have 100 samples and we build a perfect tree. On average, how many binary questions will we have to ask for each query? Let's get somebody else. You, ma'am. Yes, which base? All right. You get an extra bonus prize. Good job, yes. So what does that work out to be? 6 or 7? Okay. Right, so it turns out that that's pretty fast, right? If now say we go to 1,000. What's log base 2 of 1,000? Huh?
1024 is 2 to the 10.
10. So with 1,000 elements, we only have to ask 10 questions. And binary questions are really, really fast. processors are optimized to do that quickly. Also, if you're using a GPU, the sort of topography of decision trees is well suited to GPUs as well, so it can be very, very fast. Now, decision trees are slow at learning time because it takes a lot of computational effort to build one of these trees, and that's what we'll talk about Tuesday. I want to raise a couple more points before I let everybody go. Sometimes we repeat factors in the tree. Remember that. Not all factors are guaranteed to be used. And one last question for thought. When I asked you, how many questions we'd have to answer for a 1,000 element tree, you all said log base 10 of 1,000. You're making an assumption. What's the assumption that you're making about the tree? It's a binary tree. That's one. There's another assumption you're making.
Complete tree.
Huh?
Complete tree. There's all the depth is the same for each path.
Right. So another code word for that is balanced. It's a balanced tree. So a lot of the algorithms involved in building these trees strive to keep them balanced, and that'll be something else we talk about. I'm gonna real quick and see if we have any questions online. The only question we have is if I could move the camera closer to the whiteboard. So too late for that. Any questions here about the assignment due Monday? Yes.
So we're expecting to maximize the Sharpe ratio for a portfolio, and assuming that stocks have the same gain over time, the same cumulative return, your optimization step is going to be minimizing the standard deviation of your average daily returns. That's right, assuming that the cumulative return is the same.
Okay, I'll try and restate what you're saying. Suppose we have a portfolio of 4 stocks, and no matter what allocation we give to them, the cumulative return will be the same, but the standard deviation may change.
Yes.
In that case, yes,
Well, that's not my question.
we're trying to minimize standard deviation.
Yes. Now, to do that, if you had 2 stocks that literally just did the opposite of each other,
Right.
you try to do 50-50, right? Because then your average daily return is constant.
Right.
Why does that mean anything? Like, why is that important? Why is that something to do? Or is this?
Having 2 stocks that are anti-correlated to one another is a wonder of nature. There's one other thing you want, though. You want them on the short term to be anti-correlated, on the longer term for them to be correlated up. That's a thing of beauty. But you'll have to wait for me to tell you why. Okay, goodbye in TV land. I'll be on Piazza to answer questions. See you all Tuesday. Hi, everybody. Welcome. Sorry for my delay in getting started. I make some of these videos from my basement, and I got down here to discover some of my technology was missing because of a certain child of mine. So anyways, I had to find that and plug it all in. Ready to go. Okay, I will check periodically on Piazza to see if we've got any questions. One thing I would appreciate is if somebody who is currently watching could post a question on Piazza indicating that you can hear me. I'm going to start blazing forward anyways, but it would be good to get that feedback, so thanks. And I'm going to check on Piazza right now. Okay. Okay, somebody says they can hear. Thank you. All right, I'm going to now step through some PowerPoint slides. Okay, let's see what happens when I go full screen on this. Oh, I can't. Okay, I'm going to change things. Give me just a moment here. Okay. Okay, put together a couple PowerPoint slides I'll step you through. So if you remember the last lecture, we talked about if you had a decision tree, how you might use it. So in this lecture, we're going to talk about, okay, how do we build that decision tree in the first place? So let's pause for a second and think about what are the things that make up a decision tree. Big picture, remember here, we're trying to build a model that from some factors or features or attributes, things we can measure about a system, what is going to happen later. And so the factors or attributes are our X's, and we might have many of them. We might have up to N of these factors. Now, associated with each group of factors are a label, Y. So our data consists of the values of the factors and the values of the labels. Think about it like a big matrix where the columns are the X's and then that last Y, and the rows are individual samples of data. So each row might represent a day for a price of a stock, or each row might represent a day of weather. Then using that data, we build a decision tree, and the decision tree consists of decision nodes. Each node represents a binary decision. Now, we can build decision trees that aren't necessarily binary. They might have more than 2 outgoing edges. But for simplicity, and actually it turns out for efficiency, it turns out that building binary trees is the best way to go. So we're only going to have 2 potential outputs of each decision node. There's then the outgoing edges that lead to additional decision nodes. And there are 2 kinds of special nodes. There is the root node, which I forgot to mention here, and also leaves. So when you finally reach a leaf at the very end, that's the value that you're trying to predict. The root is the first node at the very top that you start at when you're trying to make a decision. And we build these decision trees from data examples. And again, we have each row in our data is a set of X's and a Y. Now I'm going to double check that you all are able to see my PowerPoint slide. I don't want to get all the way through this and discover that people aren't seeing the slides. So I'm going to go take a quick check at Piazza. Okay, people must see the PowerPoint because they're asking if they can have it. And the answer is yes, you'll be able to have it. I'll come back a little bit later to answer some of the other questions that are popping up. Great, thank you very much for answering. Okay, here's an example decision tree. We've identified the root here up at the top. So whenever we want to query our model to see what the value, what the predicted value is, we start here at the root, and each decision node asks a binary question. Is this factor x11 less than or equal to 9.9? If it is, yes, we go down this left edge and we come to another question about that same factor, x11. And if it's less than or equal to 9.25, we go to the left. If it's not, we go down to the right. And here we see a new factor that we're asking questions about, x2. If it's less than or equal to 6.48, boom, we go down here. We arrive at a leaf, and the value is 6. Now, a couple things I want to point out. This is an example tree. I'm going to actually show you in a few minutes how we built this exact tree, and it's using that wine data that I introduced the other day. So X11, for instance, is percentage of alcohol. I forgot what X2 is. But thing to note here is this particular tree was only built using 2 factors, and in some cases, the same factor, well, in all cases, the same factor appears multiple times through the tree. So, for instance, factor 11 appears here and here. So if we go down this branch, we end up asking 2 questions about factor 11. If we get on this branch, again, we end up asking 2 questions about factor 11. So we can repeat factors. Sometimes not all factors are included in the tree. And sometimes some factors appear more than others. And it turns out that that's often related to how predictive the individual factors are. Now, this is one way to view a tree. We can also view it in a different way in a tabular view. And this data right here represents the same tree, but in a tabular view. And this is the way I want you to build your decision tree for the next assignment. I want you to use a NumPy array, and I want you to consider these 4 columns. The first column is for that particular node, which factor are we considering? The next column is what is the split value? In other words, which value do we decide to go down a left branch or a right branch? And then these 2 other columns tell you where in my matrix here does the next part of the tree begin. So here we're saying the left tree starts in the next row, and the right tree starts at the 8th row. Now, leaves are special entries, and so if we have here in the first column an indication that it's a leaf, the next column, split val, instead of it representing a value to split on, it represents the value of the leaf. And it doesn't really matter what's in the left or right columns here for a leaf because we're not going down further. One more thing I want to say, yes, in this example, we have sort of text in this column, but NumPy arrays can only be numbers. This is just for sort of clarity. So, instead of saying X11 here, you would put the number 11. And instead of, putting leaf here, you would put some special number that signifies to you that this is a leaf. And again, these are dual representations. They represent exactly the same information. The root node is always the very first row in this ND array, and then you can see here where the left and right subtrees are. So that's how we represent a decision tree, or at least my recommendation on how you ought to represent it for your project. Now, those who have sort of an object-oriented bent and want to do things in an object-oriented way, you can do that in Python. But let me suggest again, first do it this way, get it working, and if you want to go forward with the object-oriented approach, that's fine, but get it working like this first. Now I'm going to take a quick look back to Piazza, see if we have any questions, and then I'll go on with the presentation. Okay, people see the slides. Abida asks a question. Building binary trees is best in efficiency in terms of building to the tree, you mean. Why is it? Why would a higher branching number be worse? I meant actually that if the tree is binary, it is likely a little bit easier to process. Keep in mind each question. So think about efficiency in terms of a CPU. If our questions are simple comparisons, that's something that modern day processors can do incredibly fast. So if it's a binary tree, they only have to do a single comparison at each node to decide what to do next. Now, there's probably, you can probably dig up papers that might contradict what I'm saying. So I'm not going to assert it too strongly. But I will say they're definitely easier to build. And it's my intuition that they're probably fast as well. But yeah, sure, maybe higher branching factor could perform better. The video of the slides is too blurry to read sometimes. Okay, I understand. I'm going to share the slides and also the PowerPoint spreadsheet that I'm going to use shortly. I'll put that up on the website so you'll be able to see the PowerPoint as well. Somebody is enjoying Porto. It's Patrick. Hi, Patrick. So keep in mind, everybody can see my screen right now, but I'm with you, Pat. Glad you're enjoying it. Oh, and by the way, he's checking out, he's doing an ops test, ground truth on the upcoming problem. In numbering nodes, I see you're going by depth instead of breadth. Indeed, it doesn't matter. Actually, I'm going to get to that in a little bit, and you'll see why they have the numbers that they do. So ask that question again if you don't understand it, or if I don't make it clear coming up. Okay, and let me go on with my PowerPoint presentation. Okay, here is the algorithm for building a decision tree. This is the algorithm initially proposed by J.R. Quinlan, and there's a link to this paper actually on the project wiki site if you're interested. It's actually a very good paper in the sense it's well written, it's not filled with jargon, it's easy to understand the motivation for how decision trees are built and so on. Key thing, so I know that most people in OMS are come from a computer science background, so they're probably familiar with recursion. Some of the people taking the course on campus are from other disciplines and actually hadn't necessarily seen recursion before. But this is a recursive algorithm, and in other words, the algorithm or the function called build tree actually calls itself. And an important consideration in any recursive algorithm is you have to be sure it's going to terminate, because otherwise it'll call itself over and over and over again, going to essentially infinite depths and never stop. So the very first thing that we do is a couple checks to see if we've met a stopping criteria. Now, as you, by the way, I want to emphasize that this is not the final, totally complete description of how to build a tree. This is kind of a outline, and you're probably going to find that you need to add a few more details, okay? But this will give you a good start. Anyways, the first things we check are stopping criteria. So when we get called, when this function build tree gets called with data, which is the data we're going to use to build the tree, and by the way, this is structured as an ND array where each column represents a factor, and the very last column represents the label or the Y value. So we take that data in, and if the number of rows, in other words, shape of 0, that's the number of rows. If there's only one row, that means we're being given data, essentially one sample of data. So if we're asked to build a tree out of one sample of data, well, the answer is it's a leaf, and the value of that leaf is the Y value of that data. And I'm using the same columns here that we had talked about before in our columnar data structure. The next two items don't really matter. So we create a single row that is, again, we designate that it's a leaf, the label is Y, and we don't care about the other two items. So that's one stopping criteria. Another is, what if we get called with some data and all of the labels are the same? Well, obviously there's no point in creating a more detailed tree from this data because we know what the answer is going to be. We know it's going to be just Y. So again, we can create a leaf and return it. So those are our stopping criteria. Now, if neither one of those conditions are met, then we have real data that we can build a tree with. So first step here is determine the best feature to split on. So as an example, if we're getting called for the first time to build a tree, say using the wine data, this question is essentially, what are we going to build? What is that first question that we're going to use to build our root node? Now, it turns out that each subtree is formally a tree as well. It has a root, it has leaves, it has directed edges, and so on. So we can imagine each subtree as a tree by itself. But the very first time we do this, we're looking at the root node. I'll talk in a minute about how do we determine that best feature. There's a number of different ways to do it, and it merits its own slide for discussing. Okay, now that we know which feature we're going to use, we need to determine what particular value are we going to split on. And the standard way to do this is to look at our data, look at that column I. Remember, that's the feature we decided to split on. And we look across all of our samples and we take the median. That is, the median is the value that divides the data in half. In other words, half the data is going to be less than the median, half the data is going to be greater than the median. There are special edge cases that people probably ask about. What if the same value is repeated 10 times in the middle? So you're going to have a sort of lopsided split of the data. Yeah, that's true. No big deal. Okay, so we know our split val. Now we need to gather together the data that makes up, that we're going to use to build the left side of our tree, and gather together the data that we're going to use to build the right side of our tree. And here's how we do it. And this is showing some of the real power of Python. So again, we're going to call our own tree building function here, build tree. And the left tree is going to be built from data that from the data that is less than or equal to the split val. And so this expression is called comprehension. And you can specify, okay, look through my data, find all of the elements where this column is less than split val, grab those columns out of data, and we will use that to build our left branch. Same thing for the right side, except we're using those rows that are greater than split val. So each of these, we'll call build tree in turn. So what'll happen is we'll recurse down the left side of the tree, and we'll go down and calculate this left tree, and boom, it'll return, and we'll have the value here, left tree, which is a ND array. Similarly, for the right side, we'll have right tree. So now we have two sides of our tree, the left tree and the right tree. We still need the root, and here's how we compose the root. So first element here is what's the feature we're going to split on. We determined that's I, right? The next column is what's the value we're going to split on. That's split val. It turns out that in our formulation here, that the left tree always begins at the next row. And one thing I want to mention that I didn't mention when I was talking about our data structure is these left and right columns. It turns out that it's easiest if you think about them as being relative. So in other words, this is saying that the left tree begins in the next row. So wherever we are in this, whatever row we're at in the matrix, we're saying the left tree starts at the very next row. Where does the right tree start? Well, we have to make room for our left tree. So we check to see how many, well, you know what, it occurs to me that this should be shape of 0. In fact, I'm going to just fix that right now, because that's how many rows are there in the left tree. So I got that wrong. Okay. So this is saying, okay, we got to make room for our left tree. I'm sorry. Yeah, we have to make room in our left tree. And then the next row after that is where our right tree begins. Then we append those all together. We append our root, our left tree, and our right tree. Boom, that's our whole tree. Ta-da, the end. Okay, I'm sure there's probably some questions percolating there now, so I'm going to go back to Piazza and check and see if we have any questions. Again, Abadah with another excellent question. Are we using median to make it as close to being log base 2 height as possible? Yes, that's right. So we're, put another way, we're trying to keep the tree balanced. So if at each level we split the data exactly in half, then the levels below we'll split it in half and so on. And as we go on down at each level, we'll be splitting the data appropriately so that the trees will, or the branches will remain balanced. Now, you can't always do that perfectly, but yeah, that's the general idea. Where is the root in the node? In the code. Where is the root in the code? Ah, okay. Yes. So when I was giving this presentation yesterday on campus, I defined the root, I think, up here. It turns out that you have, as soon as you determine which feature to use and which split val, you already have all the information you need to define the root. It's, you know, the first column is going to be the factor. The second column is going to be the split val. The next one is always going to be 1 because the left tree always starts to the left. And you don't know until this line, until you do this computation, how large the left tree is. You could determine it by essentially executing this, but you don't know how many rows are in the left tree until you do this, because the data size may be a little bit different. Okay, so that is how to build a tree using Quinlan's approach. Now let's talk a little bit about how do you determine the best feature. So in general, what we want to do is we want to start with the feature that segregates the data the best. So imagine for a moment that we're doing classification. In other words, we're trying to decide, is it a buy or a sell for a particular stock. We would like to find that first feature, that root feature that groups, that splits it into the most similar groups. In other words, one group should be mostly buys and the other side should be mostly sells. So which factor can help us make that split most effectively? Then we go to the next problem of, okay, now I've got a group that has mostly buys. How do I distinguish, those few sells from the other buys? And hopefully there's another feature at that level that'll help us make that distinction. So at each level, we want to somehow choose the feature that does this separation most effectively. And one way of thinking about that, or one term folks use to refer to it, is information gain. So which factor provides the most information about our data? And there's a number of different ways to evaluate that or estimate it. I believe the original Quinlan paper uses an approach called entropy. Even if they don't use entropy, that still is, I think, nowadays widely regarded as the most effective method of selection. Entropy is just a way to measure, once you've segregated your data into groups, to essentially measure the diversity or randomness of each group. So, as an example, if each side, had 50% buys and 50% sells, then we didn't really gain any information, because it still is kind of, randomly distributed. However, if one side is all buys and one side is all sells, that was the biggest information gain we could possibly get. And there are ways to measure entropy even for non-classification examples, where our data, instead of it just being labeled a buy or a sell, is a regression sort of problem. Now, don't fear, I'm not going to make you calculate entropy. We're going to use, for this project, we're going to use correlation. And it turns out that correlation actually, for regression problems, is very closely related or correlated with entropy. So what we can do is we can look at each factor in our data and see how well correlated it is with our labels. And the factor that is most strongly correlated is going to help us make that split most effectively. There's yet another method called the Gini index that is essentially another measure of diversity that people use as well. Anyways, to summarize, I think entropy is sort of the de facto standard, works very well. If you were to download and use the decision tree library in SciPy, you would find that they use entropy. I think you can choose between entropy and Gini index. I want to emphasize, though, for this project, you're not allowed to use the SciPy library. Sorry, you have to write your own. Okay, I'm going to now show you, I'm going to give you an example of doing this with real data. Let me check and see if we've got any questions before I do that. In the build tree algorithm, what does the append work? So for ND arrays, so look up the documentation for NumPy, and in particular ND arrays, and you'll see what append does. Basic idea is it takes root, it creates a new array out of these three arrays, puts root at the top, next left tree, finally right tree. You may need to provide an additional argument, essentially telling it along which dimension should these arrays be appended together. The default, I believe, is axis 0, which is rows, so you probably don't have to do it in this case. Anyways, that's what append does. It makes a new ND array out of your component ND arrays. Okay, let me now give you a concrete example. Okay, this is also the example, by the way, the graphical tree that I showed you. This is the same data in the same tree, and that data, by the way, is I started with just 8 samples of data because, obviously, I'm not going to sit here and do a 1600 node tree. So I randomly selected 8 rows out of the actual wine data. And then I picked arbitrarily 3 columns or 3 factors for it to build this tree out of. But keep in mind, for the real data, you've got 11 factors. So the data that you're going to be building your trees with, you're going to have potentially 11 factors. Anyways, factor 11, by the way, is alcohol content. And I don't recall what factor 2 and 10 are. But anyhow, each row here represents one sample of, a person scored a glass of wine. In this case, they scored it 4 out of 10. And the quantitative measures for that glass of wine were these 3 values. This represents another glass of wine and potentially a different person who tasted it and their scoring. Okay, so our first question here, okay, we're going to build a tree. And by the way, over here, I've got space set aside that we're going to fill in. This is going to be our indie array that represents our tree. Our first question here is, which factor should we split on? What's going to be our root node? And another way of putting that is, what is the most information providing factor? So one way to do that is to use correlation. So each along the top here, each of these values represents the correlation of this column of data with Y, with our labels. And I just use the Excel correlation function here. So correl, short for correlation of this column with that column. Now, you'll notice that this one is negative. It still is valuable information. All that it means is as this factor increases, Y decreases and vice versa. But it still is providing us information about Y. Now, if you look at these 3, we see that X11, factor 11, has the highest correlation. So we're going to choose that to make our root node, to do that first split. And by the way, when I share this spreadsheet with you, all these tabs along the bottom, you can think of sort of like different pages in a PowerPoint presentation. Okay, should add another row up there. Okay, so we've started to fill in our data structure here representing our tree. The dogs are barking. Don't know what they're barking at. Anyways, so we know we're going to use factor 11. Next question is, what should the split val be? And remember, we talked about using median. So easiest way to compute median is first we sort our data. So I've sorted now all of these rows according to this column. It turns out that you don't explicitly have to do this in your program because you can do that comprehension method I mentioned a moment ago. But anyways, if you sort, it becomes clearly evident what the median value is. You just want the particular value that'll split the data in half. So we go from 9.8 to 10.0, so our split value is 9.9. Okay, I need to take just a moment to make sure I've got electricity for my laptop because I'm running a little bit low on battery power, so give me just a second. I apologize for the delay. Okay, we have power. All right, so I'm indicating now the data that's going to make up our left subtree here in red and the right subtree there in green. Like I said, we already know where our left subtree is going to start. It's at the very next row. So it's going to fill up this part of our data structure. I'll move the right subtree down a little bit so we have some room to think up here. Now we're calculating the correlation with this subtree. So for instance, this now represents the correlation of the data in our left subtree with Y, and so on. So we're not looking at the whole data set anymore. We're just looking at the left subtree. So we've recursed down into calculating or computing the left subtree. Again, interestingly enough, this same factor, x11, has the strongest correlation. So we're going to use that again to split on. And it turns out it's already sorted according to that factor. So it's going to be between these two values. So it'll be 9.25 will be our split val because that's the median here. So now we have we've split the data in two now into we're going to compute a left subtree and a left right subtree. And again, we need to calculate in each case what is the correlation of each column with our labels Y. And by the way, we've added another row here, which represents that decision node. We're going to split the data on factor 11 again, and we're going to use 9.25. Now, something to observe here is when you get down to the point where you've only got two data elements, it's very likely that you're going to see correlations of 1 and -1 for each factor. And there's a question of, okay, in general, if they have the same value, how do you decide which one to split on? There's multiple correct answers there. One is select randomly. Another is deterministically choose the first one, or deterministically choose the last one, whatever. I recommend that you go with a deterministic approach because we're going to have plenty of randomness in this data and in these trees anyways. It's not really necessary to arbitrarily add randomness here. And you'll see in a moment some ways that we inject randomness into this. Okay, so we selected our root node. We're now building the left subtree using that root node. So this now represents the overall left subtree. We're now going to look at building the left subtree of the left subtree. And I'm going to arbitrarily choose factor 2 here as our split val. The median here turns out to be 7.48. And now we have all the information we need to add our two leaf nodes. So if x2 is less than or equal to 7.48, well, that's this leaf, and we know the value is 3. Boom, we fill that in. Otherwise, we'll go to the right, and it's this leaf. Value is 4. We similarly, pop back up now and do the same thing with the right tree. I should say the left-right tree. And now we've completed the whole left subtree. Now, this is an error. This should be 2. Okay. One thing I want to point out here, let me make sure I'm consistent here. Yeah. The numbers I'm filling in here to point down to the essentially the rows at which the next subtrees begin are relative. So this 4 means, for instance, that the right subtree begins 4 rows down. So 1, 2, 3, 4, it's starting here. This 2, for instance, means the right leaf is 2 rows below, 1, 2. So these values are always relative. The reason for that is it makes bookkeeping a little bit easier when you're traversing the tree, to do a query. It also makes it a little bit easier when you're building the tree. You could still make them absolute references, it's up to you, but you have to pass around some more information to keep track of where you are in the tree. Doing it this way, you don't ever really have to know where you are in the tree as you're executing the algorithm. Okay, so now we've fleshed out the complete left-hand subtree. Then we start working on the right subtree, and let me just skip to the end. It is a long and boring story to go through the whole thing, but here now finally is our entire data structure describing the tree. So that's how you build a decision tree from sample data. It's one way. I'm going to give you another way in just a moment, but let me now go check and see what questions we've got. Okay, no new questions. Let me reload here just to be sure. Okay. Let me now show you a different way to build a tree. So let me, before I show you that, let me ask you to think about something for a while. I want you to we'll take a look at this original definition of how to, or description of how to build a tree. Which of these steps in this algorithm do you think are expensive? Obviously some are more expensive than others, but in particular, which one is probably the most expensive? I'll be quiet for a moment while you ponder that. And I'm having a sip of wine myself. It makes the lecture better. Okay. Certainly, one of the most expensive things to do is determining this best feature to split on. Why? Well, in the method I presented, if we're using correlation, calculating the correlation, say for 1,600 rows, NumPy can do it quickly, I admit it, but it still, of all the things we might do, is one of the more expensive. And we have to do the correlation for each column of data before we can decide what to split on. So if there's one way that we could, one thing that we could do to speed up our algorithm the most, it would probably be to make that part faster. Another one is computing the median. Now, in the example I gave, I showed that you should first sort the data and then find the middle values, and that'll help you compute the median. It turns out there's faster algorithms now that actually can compute the median in order in time. You don't actually have to do the full sort. Median is order in, but it's a big in, so it can take a while. But anyways, long story short, if we could figure out a way to do these two steps faster, that would overall help our algorithm be a lot faster. And that's exactly
where random trees come in. So let me skip to random trees. So, oh, and I need to fix this. Okay. This is an algorithm by Adele Cutler. She was a PhD student of Bryman, who was at UC Berkeley, and he was he took J.R. Quinlan's ideas of creating decision trees, but expanded the idea greatly with random trees and random forests. And Ms. Cutler, who's now a professor in Utah, produced, I think, one of the best papers describing their methodology. And she's carried it forward in a number of different ways. But anyways, the general idea is this. Rather than burn all of that time trying to decide what the best feature is to split on, let's choose it randomly. Clearly, picking a random number, pick a random number from 0 to 10 is a lot faster than doing the correlation on 10 columns of 1,600 pieces of data. So that speeds things up significantly. Now, you might naturally ask, yeah, it probably does make it faster, but doesn't that screw up your tree? So postpone that question for a second, and I'll answer it in a moment. The initial answer is yes, it does impair the quality of the decision tree, but there's something we can do to work around that. I'll get to that in a moment. The other thing she does is, rather than compute the median and having to sort or run the select algorithm, you just choose a random row, 2 random rows, grab the feature value out of those rows and take their mean, or just divide them by 2. And that gives you, that's guaranteed to give you a split value that is somewhere, not at the edges of the data, it's somewhere in the middle. It might be towards an edge, but it's definitely not going to be at a very edge. So these two random selections here make the tree building algorithm monstrously faster. You still then have to go through the rest of the algorithm like I described before, but these 2 random selections make it much faster and much easier. Okay, now back to this earlier question of, well, doesn't that impair the quality of my tree? The answer is yes, if you have only one tree, but something we're going to get to shortly, either later this week or early next week, is something called bagging. And in general, the idea here is it's better to have a learner that is composed of many learners. Another term for that is ensemble learners, than just to have a single learner. So if you have a single tree and you build it carefully, using this Quinlan method, yes, it can do very good. But if you have a learner that's built of multiple trees, even if they're created randomly, its performance can actually supersede that of the best individual tree. And we'll get into more detail on that a little bit later. But essentially, a random forest is a group of trees where each tree is computed somewhat randomly. Now, I want to mention something about this randomness. There's several different ways that you can cause this forest to be random. One of them is each tree is computed, with these random numbers here. Another is that the data that you construct the tree from could be selected randomly. So you're given a whole set of data from which to create a learner. What you can do is subsample, randomly select not all of that data, but some subsample of that data, create a tree, resample, again, it's with replacement. You pick another group of data, build another tree, and for each tree you build, you grab some random assortment of that data. So even if you're building, say, the Quinlan type tree that isn't random at all, each tree that you build is built from a different selection of the data, so it's going to be a bit different. And it turns out that these differences are important. If all of your learners are identical, there's really no benefit to having multiple learners. You want essentially uncorrelated learners or diversity among your learners. So that's why these random approaches end up, when you combine them into an ensemble learner, give you a really valuable system. Okay, I'm going to check one more time for questions, and then I want to wrap up with strengths and weaknesses of decision tree learners. Let me check for questions here real quick. Never mind. Okay. Okay. Glad to have you all participating, by the way, at this late evening time. Okay, strengths and weaknesses of decision tree learners. So whenever you're a learner, you should look at a few things. Let me actually build this list while I'm talking about it. Cost of learning. If you compare, for instance, decision, what's the expense of creating a decision tree compared, say, to creating a KNN learner? So we went through, this fairly complex algorithm about how to build a decision tree, and as you can see, it can be expensive. KNN, K nearest neighbors, is simple at learning time. You just take the data and plop it into RAM, and you consult it later when you're doing queries. So in terms of cost of learning, decision trees lose to K nearest neighbor. I would say also that linear regression learners, they're somewhere in between. To build a parametric model using linear regression takes a little bit longer than it does to just save things to memory like KNN, but doesn't take quite as long as it does to build a decision tree. And for building a decision forest, you got to multiply that by however many trees you're going to have in your forest. Next is cost of query. So among these three algorithms, K nearest neighbor, linear regression, and decision trees, I want you to think for a moment. I'm going to ask you a question. Which is the fastest? KNN, linear regression, or decision tree? In other words, we've got our X factors, and we want to say, hey, what's the predicted value? What's the predicted Y using this data? I'll pause for a second, let you consider that, and then give you the answer. Linear regression is the fastest. All you've got to do, if you have a linear regression model, it's just a set of parameters. You just, x1 times parameter 1, x2 times parameter 2, add them all together. Boom, that's the answer. It's blazingly fast. So in many cases, linear regression learners don't have such a high quality in terms of, what's the prediction versus the actual result, but they are blazingly fast to learn and blazingly fast to query. KNN is the worst of them all because when you're querying a KNN learner, you have to compute the distance from your query to all of your individual data points, then sort them and find the closest K data points. It's extremely expensive to query a K nearest neighbor learner. Decision trees, again, are somewhere in between. The beauty of them is because they are binary trees for, say, 1,000 elements, on average, you only have to ask, I think, I know Pat calculated it for me, whatever log base 2 of 1,000 is. I don't have log base 2 here. I think it's, what is it, Pat? I think it's about 10. Anyways, so if you build a tree with 1,000 samples, to query it, you at most have to ask 10 binary questions, and that's really fast. Again, decision trees are somewhere there in between. Now, there are some strong benefits of decision trees that I want to mention here. One is you don't have to normalize your data. So I believe in one of the online lectures, I hope, if we don't, I'll have to add one. We talk about this problem of, let's suppose one of your factors ranges from 0 to 1,000, and another factor ranges from, say, 0 to 1. It turns out that if you build a k nearest neighbor type model from that data, the factor that ranges from 0 to 1,000 ends up overwhelming the other factors and turns out to just be the most important factor, even though it may not really be the most important factor. So typically with KNN, for KNN learners, you have to do something to normalize your data so that each dimension essentially has the same range. So typically you take the mean of all the data for a factor 1 and normalize it to that mean and standard deviation. You don't have to do that for decision trees. They automatically determine what appropriate thresholds are as they build the tree. Let's see. Just trying to think of the other benefits of decision trees. I'm sure the ones I mentioned the other day will occur to me as soon as we finish this, as soon as this lecture. I'll add them to this presentation later on. Anyways, that concludes my lecture to you on how to build a tree. I'll do one more check on Piazza to see if we've got any more questions, and then I'll wrap it up. Pat adds a link to scikit-learn and pandas. I believe he's pointing to something that lets you visualize a tree once you've created it. That's nice. And thank you, Pat has provided log base 2 of several numbers for me. Thanks. Okay, getting to this last question. The reason we don't have to normalize the data is each variable is treated the same weight, and it's based on correlation or entropy to decide the best split. Yeah, because yeah, good point. We're essentially looking at correlation to decide which factor to use, and then yeah, we use the median to decide the split value. So there's no additional benefit in normalizing it first. If in the case of KNN, if you didn't normalize it, like I said, that particular factor that varied over a wide range would become the most important one. Okay, doing one more check for questions, and then I'm going to wrap up. Okay, thank you everybody for your attention. I am going to go ahead and close up the presentation, and yes, I will post these slides to the wiki. Oh, this is kind of fun. Okay, anyways, let me stop that, and I'll stop the broadcast. Bye-bye, have a great evening, and see you in TV land.